Hey guys, this is Matt Kids 101, and today I'm going to be making an experimental math video for some math sessions. So leave a comment below if you have any requests or what you think about these math series, or of course if you have any questions about the video. So today I'm going to be proving Euler's identity, which is that e to the I theta is equal to cosine theta plus I times sine theta. So I'm going to do this by by solving differential equations by separating variables. So there's other ways of doing this. That's how I'm going to be doing it. I think that it's clearer than using a Taylor series. So I'm going to let y equal cosine theta plus I sine theta. So y is equal to the right side of the statement, and I'm going to prove that it's equal to the left side of the statement. And I'm also going to keep in mind that y of 0 is equal to 1, because that's going to come in handy later. Cosine of 0 is 1 plus sine of 0, which is 0. Okay, take the derivative of both sides with respect to theta. So it's going to be dy d theta is equal to, the derivative of cosine is minus sine theta plus I, derivative of sine is cosine theta. Alright, now I'm going to factor out an I, so that is equal to I times, so I squared is going to be negative 1, so if you bring out an I, so this is going to be I sine theta plus cosine theta. So if you look back, this is exactly what we defined y to be. So it's equal to IY. Alright, I'm just going to write that there because we're running out of space. So dy d theta is equal to I y. Now I'm going to divide both sides by I y and multiply both sides by d theta. So we have minus I times 1 over y dy is equal to d theta. And 1 over I is equal to minus I, because you can say that 1 over I is equal to I over minus 1. And so I squared is minus 1, and then when you cross multiply. So that's an easy way to check that that holds true. Alright, so I'm going to integrate both sides. I'm going to use an indefinite integral, but there might be other means of doing this. Alright. Now, when I do this, I'm going to get minus I times ln of y is equal to theta plus some arbitrary constant. And now, all we have to do is isolate y, solve for the constant, and check what that's equal to. So I'm going to let Alex do that part.
Alright, so now I'm going to be putting the final touches on this proof and showing you that y is actually equal to e to the I theta. Okay, so first off, we have this situation right here with an ugly I on an ugly constant there, and we got this I on that side and the natural log of y here. So the first step is going to be to isolate y. So in order to go about this, first we're going to get rid of this minus I. And to do that, we just are going to multiply both sides by I. Because if you do that, you have I times I and then minus that, so that's minus minus 1. So we just get the natural log of y. I'm just going to write what I did there. I multiplied by I. Is equal to I theta plus I times some arbitrary constant is just some other arbitrary constant. And in this case, the arbitrary constant is probably going to be complex. We don't know what it is. So I'm just going to keep that as C, but you really know this isn't the same constant. It's the original constant times I. And now we can just do e to the both sides. So if I do this, then that gives us e to the natural log of y is just y. So it's y equals e to the I theta, which is ultimately what we want to get, plus c in the top part. And so in order to prove that this is equal to that, we really just, all that's left is to prove that this arbitrary constant right here is actually indeed 0. And to go about doing that, we just need to use our initial condition that we said initially up there. So if we say that y of 0 is 1, then e to the I times 0 plus c, since this is still our y function, has to equal 1. And I times 0 is 0, so e to the c equals 1. Then we take the natural log of both sides. C equals the natural log of 1, which is equal to 0. And so now using our initial condition of this function, we prove that y has to be e to the I theta plus 0. So thus, from here, it finally follows that y is equal to e to the I theta. So that's how you get rid of the arbitrary constant that comes from separating variables, and you get the final equation for y.
Alright, so now that Alex demonstrated this, right before I end the video, I'm going to show some cool properties that are useful about this. So the first is an equation that you've probably seen before, but what happens if, now that we know this is true, what happens if theta is equal to pi? So on the left side we have e to the I pi equals cosine of pi is -1, and then I times the sine of pi. Well, sine of pi is 0, I times 0, 0. So e to the I pi is equal to -1, or e to the I pi plus 1 is equal to 0. So this is e's, pi's, i's, positive 1s, 0s, all the fundamental constants in math, multiplication, exponentiation, like the whole shebang. So another cool thing is if you want to take I to a power, that might be hard to do, but with this it should be pretty easy to do. So let's take a look. So if we have e to the I pi is equal to -1, so then you might want to, well, -1 is equal to I squared. Alright, so then you can take the square root of both sides. So, well, you can take both sides to the 1/2. So then e to the I pi over 2 is equal to I. And then if I want to take, like, both sides to the I, like, let's say I want to take I to the I. So then I could say I to the I. Normally that would be pretty hard. I would have no idea how to do that. But in this case, it's going to be e to the I squared pi over 2. I just brought both sides to the I. And I squared is -1. So I to the I is e to the minus pi over 2, which is real. So I'm going to leave you with that to think about. Alright, thanks for watching. Subscribe and goodbye.